that we'll present on, and also instructions. So these are all things that I shared at different points over, the last 2 or 3 days. Well, the paper I assigned last week, and the dates and guidelines for presentation I shared Sunday and Monday. So it's all in the discussion forum dedicated to that. So let's use that discussion forum for communications that are related to the presentation, okay? So unless you reach out to me with questions, I assume everything is clear to you and you're good to go with presenting on that day and you're working on it, okay? So now to the lecture today. Today we are going to talk a little bit about hippocampus and memory. So we hinted at this basically the very first lecture, the introductory lecture. And I said the hippocampus is also related to memory, and it does episodic memory for humans. So, how do you relate that to spatial memories and place cells and grid cells? And I said, it's not completely clear how the two things are related, but definitely, the fact that place cells is such a neural correlate of a behavioral aspect in an experimental model of an animal, it gives us somehow like a handle, an opportunity, a window of opportunity for trying to understand how the circuits in the hippocampus might have something to do with memory. Of course, humans are not rats, but with both mammals, the hippocampus is similar structure, so we can start to think, okay, maybe it performs similar computations, and somehow understanding place cells in the rat might give us a sense of how the hippocampus works in humans too, for memories. I mean, the hippocampus, even in the rat, is involved in what you could call episodic memory in a rat. And even in humans, the hippocampus is involved in spatial memories, and it also has place cells and grid cells. So one of the presentation, I forgot who's doing it, but in one of the presentations in the upcoming week, that was going to be one topic that is covered. So we're going to have a bunch of topics that we haven't covered during the course, things like, place cells and grid cells in other species, including humans, and other types of cells, and relation to aging, Alzheimer's, circadian rhythms. We have a little bit of different topics. But today we're going to talk about memory and what we know about place cells properties that seem related to memory, so that we can use them to understand memory function in the hippocampus. Next lecture will be about time, and then the presentations and the tests. So basically, next lecture is going to be pretty much the last, classic lecture where I give a lecture, and then there's going to be presentations and the test and reviews of the test, and then the final exam. So, you might remember this slide. This was in the introduction about these men who had been underwent surgery in the 50s to remove pretty much both hemispheres of the brain, removing, not both hemispheres of the brain, just removing the part where the hippocampus is, so the medial temporal lobe, as it's called, the structures in the primate brain that included the hippocampus. And the reason that they did these operations is that he suffered from devastating epileptic seizures. And epileptic seizures is something that might have been interesting to cover in this course. But epileptic seizures usually originate in either the hippocampus is one of the places where usually they originate. And so, the only thing they could do is just to go there and remove the hippocampus. And even nowadays, if you think about nowadays, they're less blunt. So they send down electrodes in patients, similar to what I do to rats. So we studied in rats. Just send down electrodes to the hippocampus, and then monitor the activity to figure out exactly where the epileptic seizure starts, so that they go in and they lesion only that part of the hippocampus, so they don't have to lesion the entire hippocampus. And usually it is in these experiments where an electrode is implanted in a human being for medical reason that you ask for permission to the patient, say, hey, can we do an experiment with virtual reality? And you try to see if there are place cells in humans. That's how they discover something like place cells in humans. Again, this is going to be the subject of a presentation on one of your fellow students. So, but back then, there wasn't anything like that. So they just went in and removed both hippocampi. And so this person had these amazing, so he didn't really lose cognitive abilities or intelligence or anything, but he had lost the ability of forming new episodic autobiographical memories. So, anything that has to do with your events in life. And it was called what is called anterograde amnesia. Anterograde. So it's amnesia. Amnesia means like loss of memory, but it's loss of memory in the future. So the older memories, they were still there. He would remember things, but not form new memories. He also lost some of the more recent memories. It's not really that clear cut, okay? But it is this, amazing, aspect. And I think I even mentioned about a movie, Memento, that is all about this idea. And I think we talked about it in the introduction. So that's a good movie to watch if you want to understand what, kind of the idea of the hippocampus and its function. So this is the New York Times page that came out when he died, because everybody knew him as HM in the field, because, for privacy reason. So when he died, we learned that, his name was Henry Molaison, but, everybody still call him HM. So, here's a couple of slides where I put a description, an early description, 1957, so you can read about it, but basically it just gives you examples of how these loss of memory would work. So there was some partial retrograde amnesia, so he didn't remember some things about 3 years previously, or not anything of the period in the hospital, but could recall some trivial events that occurred just before his admission to the hospital. His early memories were apparently vivid and intact. Then after the surgery, he would forget about where he was living, because they moved to the new house, and 10 months ago, this was after surgery. So, they moved to a new house, and he just remembered the old house. He couldn't learn that he was at this new address. And then he would not recognize people. So anybody that was introduced to him after the surgery, after 20 minutes, he would forget that he ever met you, even if he had a conversation with you. He would have a sense of familiarity about that person. So there is obviously different functions in the brain, different parallel pathways, and not all learning and memory is all one system. But for the most part, you could have a conversation with him, he will not remember. He will not remember the doctor, the doctors that worked with him for decades, he would not learn about them. Every time it was just like meeting somebody new, even if there was this sense of familiarity. But, a mere half an hour later, a single item food he had eaten, after he had lunch, he wouldn't remember what he had for lunch. and so on. So this was a big deal because he pointed to the function of the hippocampus. But the point is, like, this man seems like a relatively normal individual since his understanding and reasoning are undiminished. Okay. And so he could still learn new things, but it was a different kind of memory. So he could learn procedural tasks. He could have motor learning. He could learn skills. And one example was the mirror drawing task, in which you are supposed to draw something, but you can only see, you cannot, there is a screen so that you cannot watch directly what you're drawing. You can only watch it through a mirror. And obviously in mirror, everything is flipped. So when you make a movement, you have to move in the other direction relative to what you're seeing in the mirror, right? So it can be disorienting at first, but people learn it and they got better. And so he would, you could see day 1, day 2, day 3, the errors that he would make, they would just drop. So meaning from day 1 to day 3, he had learned to do this task better. So it's not like every form of memory or learning was affected, just this episodic memory. So for example, he might not remember about this task. He might not remember he had done it the day before, but when he would sit down doing it, he was better at it. So one part of the brain kind of learned the task, but the part of the brain that should inform you to tell you that you have learned the task, and this task is something you don't know, because that was an episode. That was kind of an autobiographical fact that his memory wasn't able, his brain wasn't able to memorize because of this hippocampal loss. Okay, so it's fascinating, if you think about it. It's fascinating in the sense that, whatever your sense of identity, if you think about it, your sense of identity, your sense of, everything you are, in a way, is related to this narrative of your life history. And that goes all through the hippocampus. If your hippocampus has damage like HM now, you're not, from now on, you're not going to be able to keep building this life history in your brain. So it is, tragic for that individual. At the same time, it's like fascinating that there is a system like that and that we cannot know where it is for the most part. So this kind of like to give a sense that the taxonomy of memory, right? There are multiple memory systems. So you see, okay, memory, okay, there is declarative and there is non-declarative. So what does it mean, declarative? It means that you can declare it, right? What does it mean that you can declare it? It means you can verbalize it. You can consciously recollect. You can verbalize. So that's what it means. Like that's the kind of memory that we think the hippocampus is involved, at least in forming these memories, not necessarily in preserving them forever, because as we saw, HM could remember things that have happened before the hippocampus was lesioned during surgery, was removed during surgery, right? So, it seems like the hippocampus starts forming the memories, then somehow these memories are moved somewhere else in the brain, okay? At least that's kind of the classic view. There's always caveats and challenges and controversies about these things, but this is the classic view. To some extent, it captures what we know about the brain from neuroscience of memory. So again, declarative, non-declarative. Declarative means you can consciously recollect this memory, you can declare it. And so facts, events. So what is an event? An event would be like, where did you park your car? What did you have for lunch? Who did you meet yesterday? You know, what happened the day that your best friend married or whatever, you know, all these things that we've been calling episodic memory, autobiography, right? Facts are something that gets distilled in more like a knowledge of a fact of the world. So now you know that place cells are in the hippocampus from this course, right? That's more like a fact. It's called semantic memory. So it's a memory about a fact. But you might remember, oh, I learned it in that class that I took at UTSA online, you know, the year after the pandemic, or still during the pandemic. And so you remember that, that's more like an episode, right? But then now you know the places are in, you know, there are places in the brain, that's more a fact, right? So there's facts and events. It's called episodic memory and semantic memory. Should probably label it here. Non-declarative is everything else, procedural skills and habits, everything that is not declarative, priming and perceptual learning, simple classical conditioning, non-associative learning, emotional responses, skeletal responses, all these things, I would imagine that you have, you know, if you've taken a neuroscience class or psychology class, or you might have learned in other classes. We're not going to cover that. You should just know that there are different kinds of memories and declarative, non-declarative. We are just going to be on this side because of the hippocampus. Just know that, you know, there are these other kinds of memories that are non-declarative. And, you know, just have an idea of, you know, what could be procedural or not. So there are other classes. If you're interested in this class, you know, like we offer neurobiology, learning and memory, or something like that, learning and memory at the graduate level. We have this new neuroscience curriculum that we're putting together. So there's going to be classes like that. Or you can always reach out, just take a class in the psychology curriculum if you're interested in these topics. So, okay, we are here mostly. And the medial temporal lobe, diencephalon, you know, that's just the area where the hippocampus is. It's more the kind of terminology we use for the human brain. And we mostly focus on the hippocampus and the hippocampal formation, where the hippocampal formation is the hippocampus plus medial entorhinal cortex, presubiculum, parasubiculum, all the areas that we already looked at. This is a slide just to clarify a little more about retrograde amnesia, anterograde amnesia. We talked about it already. I think, no, it's pretty clear. Anterograde is amnesia for things that are learned after the brain injury. Retrograde amnesia for things that were learned prior. Medial temporal lobe, amnesics. Again, medial temporal lobe is the area where the hippocampus is. And apparently temporally graded retrograde amnesia. So they have anterograde amnesia, and then they do lose a little bit of the memories that had already been formed. But it's the more recent memories that are lost more. The oldest memories are preserved more. So that's what they mean by a gradient. So, no, sorry, what is graded? Temporally graded. So yeah, temporally graded retrograde amnesia. The strength of recollection increases with the age of the memory. What does it mean? That your ability, if you have hippocampal lesion today, your ability to recollect older memory is better for the memories that are older. The more recent ones, you know, they are more subject to being lost. In a way, if you think about it, it's the same thing that happens to a lot of Alzheimer's patients. And we're gonna, one of you will present about grid cells in a rodent model of Alzheimer. So, you know, more to follow. But if you think about people with Alzheimer, or even people like with extreme, I remember my grandmother, before she passed away, she didn't have Alzheimer per se, but, she tended to remember more the things that were going back, much back in her life. So it's obvious that somehow the hippocampus is involved. has like a continued involvement in producing this memory and generating it before they get somehow moved, consolidated somewhere else. So this is, again, some terminology: system consolidation, reconsolidation. So system consolidation is exactly what I just described, is this process by which memories over time become independent of the hippocampal medial temporal lobe memory system. And so the theory is that the declarative memories initially require the medial temporal lobe for acquisition retrieval. Over time, the memories become consolidated, presumably in the neocortex, and can be retrieved in the absence of functional hippocampus. Then, there are controversies. Reconsolidation is this phenomenon that whenever you retrieve, you recollect a memory, it's like in a way, the memory formation process is activated again. So the memory becomes vulnerable to being changed. When you recollect something, if somebody, in recollecting it, you might be able to change it, and then it goes back and it gets reconsolidated in an altered way. This is, this is something that is kind of important. It's very important, not just scientifically, but there is a lot of repercussions, for example, implications for the judicial system. If you are a witness on trial, like when you recollect a memory, if somebody already made you recollect a memory, there is all issues about potential biases and manipulation, maybe from a psychologist, from a therapist, or an expert. In recollecting the memory, somebody might cue you to change that memory, and then now it feels like it's the real thing. An example that I remember was done was about 9/11. Most of you probably are so young and they don't remember 9/11, when the skyscrapers in New York were hit by the airplanes, right? But I remember, I was still in Italy, but I remember on the news, and we all have this memory of bought skyscrapers getting hit by these airplanes and falling down. And it just feels that's what, I remember where I was, I remember what I was doing, because it's such a topical, event, right? And then somebody told me, look, the footage of the second skyscraper coming down wasn't available on the first day. It came available on the second day. So basically you cannot remember seeing bought skyscrapers on TV falling down, because the footage was only available the day after. And so it's amazing how, like, you ask most people, that's how they remember it, because they saw it again the next day, and somehow perhaps this reconsolidation occurred. But, you can make a whole lot of examples. This is something that just popped up in my mind because somebody told me, but like, it's kind of interesting. So lots of implication. It's kind of fascinating how, memory works in our brain. But so let's, the idea is just to linking it back to what everything we're doing in this course, which is like, space and time in the brain, and space and place cells and grid cells. Okay, that's what we can study in rodents, how everything is related. Does it give us any clue on, what memory processes work at the neural level, neurons and circuits in the brain. And, again, I'm going to go back to this statement by John O'Keefe and Nadell in the 70s, the hippocampus as a cognitive map. The idea was very well linked to memory. The idea was that this cognitive map was a map for, as they said, the hippocampus is the core of a neural memory system. providing an objective spatial framework within which the items and events of an organism's experience are located and interrelated. So in a way, the cognitive map, I mean, according to this theory, like especially, okay, in a rat, everything happens in this spatial framework. But even in humans, in a way, we abstract the idea of space. So if you think about how much space is recurring, in your language, when you're not talking about space, we use a lot of prepositions that refer to space. And so maybe there is something about this cognitive map explaining how memory evolved in the animal kingdom all the way up to humans. But to do that now, to make it a little more concrete, we need to study what kind of properties place cells have that are related to memory. So one is hippocampal remapping. This is something that we touched on here and there. And but now we're just going to address it in a more systematic way. So there is lots of terminology remapping called local remapping, partial remapping, complex remapping, and then more recently, global remapping and rate remapping. Global remapping and rate remapping seems to be like the end all, and that explains everything. I do not think that explains necessarily everything, but it is a good compact theory. For place cell remapping, it's believed that the kind of learning and memory that is revealed by place cell remapping is incremental, latent, and incidental. So incremental means that it happens slowly, although not all experiments show that. Latent means that it's happening without necessarily having a manifestation in behavior, which usually is the definition of learning. If you learn something, that changes the behavior. But you can change something, maybe it changes something in the brain. So the representation of place cells can produce these different maps in different environments. And it is also incidental, because it occurs in absence of an explicit reward. But let's see, this probably is a slide that I should have put later, because first we want to see what it is, right? So here's an example from an early study. Here it was an animal in a cylinder. And remember those cylinders with a cue card, white cue card, the black. Here what they did is like they put the animal in two cylinders, and one had a white cue card and the other had a black cue card. So it's kind of like a different kind of environment. And they looked at what happened with place cells, right? We've seen these experiments where we rotate the cue card and we found that place cells rotate and head direction cells to rotate, right? But here is different. Here you're not rotating the cue card, you're switching from black to white. And what happens to place cells in those two sessions? So let's see, cell one. All right, well, cell one, white here, black here, looks like the same. Notice that the color code here is different. This was in the early days, every researcher was using its own color code. So it's kind of a little confusing. Obviously, yellow means no activity. This blue here means high activity. So there is kind of a place field here around the perimeter. It seems pretty similar. So cell one really, the place field really didn't change. Now you look at cell two though, well now this changed. There's a place field here. Now the place field rotated, right? Okay, so it looks like it rotated. Cell three, well cell three maybe rotated just a little bit, but not much. So when you look at these, cell one, cell two, cell three, you can say, well, there's not much remapping. And if there's remapping, it seems like it's remapped as some cells remapped as some kind of rotation, right? But when you look at these other cells, they reveal a completely different story. So now you see cell 4, see, it was fighting here. Well, now it's fighting, there is a nice place field entirely contained in the cylinder. So this field hasn't rotated. This field has shifted probably. Now you get another cell that has a nice place field in the white card condition. But in the black card condition, it just fired a bunch of spikes here and there, but it really didn't produce a place field. It's a cell that, we would say is mostly silent in that environment. It became inactive or just got a very little bit of sparse firing. This other cell, again, has a nice place field here, and then it becomes a little more peripheral here. So, and it even seems to have rotated. So this is now remapping to this rotation. So this was called complex remapping. So there is a remapping. So like the place cell map changes. Remember the place cell map, you can think about like there is so many place cells. One fires here, one fires there, one fires here, one fires there. That covers all the environment. But now, if you do one manipulation like this, these place cells change where they fire. And if you look at it, it's not like they change all in some coherent fashion. It's not consistent because one stays pretty much where it stayed before, well, the other rotated. So obviously they didn't do the same thing because otherwise they would have both rotated. But plus, this other one, one time was active, another time was inactive. This one moved in yet another way. So each one is kind of doing a different thing. Now, a caveat is this is an early study. So these cells were not recorded simultaneously. They were recorded, from the same animal over multiple days, expecting the same manipulation. So, based on this earlier study, you cannot really conclude what I just said, but we know from Morris' studies where you can record a lot of cells that that's exactly what happened. So when it's simultaneous recorded cells, one does one thing, one does another thing. There's no way of telling. You can observe 3 place cells and see what they do during a remapping experiment. And then you take a 4th cell and look at one environment. You're not going to be able to guess what it does in the second environment based on what the other 3 cells have done. Okay, it's like they proceed in what is it called in English? Like broken rank, like not in marching order. So each goes a little bit independently. And again, this is not the study to show it because they were not recorded simultaneously, although we know that cells tend to do the same thing in a familiar environment. So probably this is what was happening here too. Now, this is more like a recent study. This was also from O'Keefe's lab, if I remember correctly. And they recorded a lot of cells. And what they've done here is that they put an animal in a square, which would be A here, and in a circle, that would be N here. And they trained the animal, familiarized the animal with these 2 environments for a very long time. And then one day, they do an experiment like the one that is shown here, in which they put the animal in different kinds of environments that are kind of transitions between a square and a circle, right? So basically, if you look at, okay, this is square, and they get 3 sessions in a square so that they can see if the place cells does the same thing when you repeat in the same environment, right? You know, like you do multiple sessions in the same environment. That's done to show that whatever you're recording, what the place field is doing, it's doing it repeatedly. So you got stable recording, the cell is producing a stable place field across sessions. But then they start using, they're morphing the square into a circle. And so they do repeated sessions with something that has rounded corners, E and J, then even more rounded corners, C and H. Then you get here is basically, what is this? An octagon. And then more so, and then you get all the way to a circle. And so they look at what place cell does. So some place cells go from silent to active. Silent to active. See, there's no fighting field in the square. And it's consistent. Every time the animal is back in the square, you know, they, wait, I have a, I got, oh, so people were on the chat, sorry. So, would the Mandela effect be an example for reconsolidation? Well, you gotta, I'm not sure I'm familiar with the Mandela effect. Stephanie, if you want to unmute yourself and tell me. Or maybe later. Can you unmute yourself? Let's see. Okay, later. All right. So back to, because so I see when people are, you know, saying something and if they're muted, and I saw a lot of activity. So I started wondering, oh, maybe they're asking questions and I'm not fielding them. Then I saw the chat, so I stopped. Anyways, go back to this slide. So you see like these cells here, cell 1, 2, 3, 4, 5, 6, 7, 8. They're all silent cell in the square. You see there's no fighting field. And even if they repeat the session, same thing. Kind of same thing in E and J, kind of same thing in C and H. And all of a sudden there is a switch when the environment start looking more like a circle. And so now you see there are place cells, there are fields there, and they kind of remain stable relative to that position up to the point it gets to a circle. Now you got other cells that were active to silent. So it's kind of the opposite, right? You know, okay, you got a place field here, stays consistent over the first 3 sessions in a square, stays consistent, but then by the time it gets to something that looks like a circle, you know, it goes silent. And then there are others that change place fields, location or shape. And again, the major change is, you know, see, abrupt switch of the map. So somehow there is, you know, the environment was morphing gradually, but the cognitive map that doesn't like that. It like, you know, it was so overtrained to recognize square or circle that wanted to fall within either one or the other. And once something in the brain sensed that this was the circle, well, then the entire place, the place fields all changed for each place cell. And again, it's hard to say what's happening to a place cell based on what's happening to another cell, you know. Say, for example, you know, some of them, they change less than others, but if you try to kind of see, okay, this one moved right or left, in general, there is not a systematic rule for that, okay? And this is unlike what we saw for head direction cells or grid cells. So the next slide is the same figure, but with the different color coding, you know, the one that we're used to, blue being silent, and red being high activity. Since the figure is so big, there are so many rate maps, and I decided to give you both color codes because maybe one is easier to look at than the other. But you know, it's just the same figure basically. So now we talk about what we just saw is basically an example of global remapping. But there is also a different kind of remapping that is just called rate remapping. So let's look at what it is. Experimentally, the way it was induced in the most famous study was for rate remapping using different platforms, arenas in the same room, okay? That's the experiment, the same room, different arena shape. And in this other experiment, they used the same arena, so the same box, but in different rooms. And when I say different rooms, you kind of know what I mean, right? Because we went through all those lectures, you know, showing, you know, visual cues. So they're very different. Maybe one has certain kind of wall cues, another has different wall cues. You might have a curtain, again, with different cues and so on and so forth. So what happens, so in a way, you know, different arena in the same room, it seems to elicit a smaller difference. So what happens is that the cells keep fighting in the same location, okay? Are they kept in the arena while the room changes? No, they're not. So these are the animals sticking out. In most of the experiments, the animal is even disoriented to make sure that, you know, it's not keeping track of this movement through the rooms. So no, they were not carried. And so in this case, you know, basically you have a circle, right? And then you have a square. To compare better, they're giving you the rate map only for a square that is inscribed in the circle so that you can kind of compare it better, right? A and A prime, right? And so you see that this place cell produces a place field in exact the same position, but you see like this field is weaker. It has a different firing rate. It fires less. It still fires only there, but the peak firing rate when the animal is in that location is lower, like it's half. Instead, this is 12 hertz, so 12 spikes per second. That means that when this red here is, it means it's 12 hertz, and here is only 6 hertz. See that the color is paler. It's not the same. It's not the same hot red, right? So that means it's firing less. This third rate map here is basically a rate map that is rescaled so that the maximum in this rate map is hot red, right? Because here is a color code, right? So here you have the hot red here is 12 hertz. So in this rate map, you can't put hot red if the cell is firing at 6 hertz. You have to put a paler code. So this paler code here, sorry, paler color here, did I say code all throughout? It was a paler color, right? This paler color here corresponds to 6 hertz here. So if you go look at a pixel that is this color here, find the pixel that is the same color here, it's on the same scale. But then to aid your visual comparison, you make a second map that is the same data as this one, but now you scale it so that hot red is the maximum in that rate map. So now hot red is 6 hertz. Why do you do that? Because if you look at all three, now you can see better. See, this field here looks almost like identical to this. The only difference is that the rate, the firing rate was lower because everything has been rescaled. Same thing here, see? It's the field has moved a little bit, but not that much. The things are never perfect, when you do these experiments. But they basically said that there is this phenomenon of only rate remapping, in which basically the place fields don't move much, but it's just the level of fighting that changes. And then in these other experiments, when they put the same arena in different rooms, they saw something that is more similar to what we saw before with the square and the circle. And you got global remapping there. They call it global remapping because now the place fields are in a completely different spot. And so you see here, they become silent, go from 20 hertz of peak rate to 1.2 hertz, meaning we just fired a little bit of spikes here and there. So you had to rescale it to see any activity. And you can see it's like what's happening here. There is just a change of what these place fields do in a way that is not systematic. And so they call it global remapping. So you can imagine and say, well, but in the previous slide, you have these circle and square, and there was global remapping, but then they didn't put it in different rooms like this one, right? So, and anyway, I can guarantee you, people like to think, oh, I found the way, that particular way that I can do the experiment, and you elicit the remapping. But global versus rate. But I think things change differently from different experiments, different laboratories. I don't think there is a rule. It's just that as long as you can show the phenomenon, you can see this phenomenon that there is remapping, and it's called global remapping. And so basically, why we think this is a form of memory is a form of memory because you have two cognitive maps in two different contexts. And they are remembered that way. So if you go back to the same environment, usually you produce the same map, okay? As we saw multiple times. But then when you change environment, you produce a different map. So there is just this neural code for space. It doesn't just represent space where the animal is, but it changes, has different maps for different environments. There is a question. Could remapping be a form of memory consolidation to reduce the effort expended? Let's hold that thought for now. Let's see what comes next. So just wanted to say that when there is rate remapping, what do in-place cells, what do grid cells do? Well, grid cells shift. Sorry, grid cells do not shift. If you look at here, wall configuration A, wall configuration B, in a situation where you have rate remapping, I'm just showing one cell, right? Because this cell is, is almost, they see a little bit of field here. The grid cell has not moved. Maybe the peak fighting in the different vertices also have changed, kind of similar to rate remapping. But the grid cells hasn't moved. You go from room A to room B and you see a place field that moves. Well, grid cells move too. So you see that now the pattern of grid cell on the left and on the right are different, while these ones are identical. So the grid realigns in a way, changes the reference frame, but grids are always active. Always remember what we said, the grid cells are always active in every environment. It's not like they go silent in one environment, but not in the other, And also remember what we said, that grid cells keep their alignment to each other. So what one grid cell does, the other grid cell does too. If one rotates, the other rotates. If one shifts, the other shifts of the same amount. If they both rotate and shift, they both rotate and shift. At least the grid cells that are part of the same grid module. Remember the modules that we see? So the grids that have the same scale, they act coherently And we saw that there is at least one theory that explains that last week, which is the attractor network formed as a toroidal model that would explain why grid cells always remain in relation to each other, same with head direction cells. But place cells, completely different animal. Sorry, shouldn't use animal, otherwise I'm in confusion. It's completely different kind of neural code. It has this ability to form, silence, scramble the map in ways that grid cells and place cells cannot do or don't do. So that would be one form of memory, which is remapping, or rather, it is what we would call a mnemonic property of place cells phenomenology. So it's a property, it's a memory property of place cells and what we know about place cells. Now we're going to look at another one that we mentioned that before, which is hippocampal replay. So hippocampal replay, you might remember, because we hinted at that, but we haven't really studied it. So the idea is that, okay, let's just say you have an animal in a sleep box. Then you have the animal running their behavior. Behavior meaning maybe they run on a track, right? They run on a track. Then they go back in a sleep box, okay? So what happens when the animal doing behavior? Well, I mean, we are experts about place cells now, right? So, you're gonna have, as the animal runs through, and here we put different colors along the trajectory just to mark the progression along the trajectory, we're gonna see a cell that spikes first, here, another cell that fires later, see, it starts firing later. There's a yellow, another kind of yellow, green, blue. So, like you take your place cells, one place cell fires here, another place cell fires there, another place cell fires there, and then you order them based on where they fire, right? These are recordings. You don't know how they're interconnected in the brain, but you can, when you visualize your data, you can order them. So I'm gonna first put the spikes that occurs in space here from this cell. Then I put the cell that fires a little forward, farther along, and then so on and so forth. So I just put the different colors, right? Oh, okay, that's what we know. Now, what happens when the animal is in the sleep box? Remember, during sleep, during inactive behavior, during certain kind of behavior that are not running around, the brain goes into the irregular activity. Remember, that was one of first lecture, right? First class, we decided all the EEG. We're gonna get back at the EEG next week, but we saw the EEG, different EEG states, right? Or logger field potential. So you had theta when the animal is running. When the animal is not running, you had things like sharp wave and ripples. And so what happens during sharp wave and ripples? Well, people looked at what place cells do, and they noticed that they fire very fast. And, like this is, maybe the animal here takes, I don't know, several seconds to go through all this trajectory. Now the cells fire a few spikes each in the same order that they fired along the trajectory. It's not perfect, and not all the time this happens, but more often than not, with a certain statistical significance, you have a prevalence of these ripples that you see in the EEG, the low pass filter signal. When you look at what the cells are doing, spike by spike, they more often than not, or rather, with a certain statistical prevalence, you'll see that they fire in an order, the same order that they fire on the trajectory. If you think about it, there's not, this is not a given, right? These cells, once the animal is sleeping, they could fire in any order during these sharp wave ripples. Because just the fact that the first had a place field here, the second had a place field here, the second place, when he's sleeping, why is the animal brain make this place cell fire in the same order that they were firing So in a temporal order, that recapitulates the spatial order. So the same order that these cells fired in space and also in time, because the animal was going through that trajectory, right? Now it's the same order that they fired during this shockwave repulse. Okay. And so in a way, it's like the animal is dreaming. So this is like really fascinating, because people think that this might give us the key to understand dreams. So in a way, it's like the rat is dreaming. You know, if you think about place cells fighting, signaling the position of the animal at any point in time and in space, in a way, the brain is recapitulating the experience of going down this trajectory, down this alley. It's like the place cell system is recapitulating that. It's like the animal is dreaming of the experience it had during active behavior. And I had transition lenses, so if there is light, sometimes they become like almost sunglasses, not trying to be cool during the lecture, but so I mean, I think this is really fascinating, and it really is something that is actively researched, and something that is very important topic, I would say, not just in the field, but in neuroscience. This actually takes in a journal called Trends in Neuroscience, right? So and this happens, I guess the next slide is just a different way to look at it. This was a slightly different experiment. So the animal was going onto this kind of track, going through these trajectories. Again, you have all these colors coded for the progression of the trajectory. You have the linearized position. So, you linearize this curve here in space. So you go from 0 to 200 centimeters traveled, and you show the firing rate of multiple cells, see, go up and down. You put them in order, spatial order. During a shockwave ripple, these fire in that order, more or less. So it is as if the animal is, again, recapitulating the experience. Now, one thing I didn't tell you is that this experience is temporally compressed in time, right? If you think about it, this bar here is 100 milliseconds. See this bar? So this means 100 milliseconds. So everything happened in about, let's say, 150 milliseconds or something like that. In the previous slide, same thing, 50 milliseconds. So, here we have about maybe 200 milliseconds. So, but the animal takes longer to go through that trajectory. So it's like when you're dreaming fast, right? And so this is actually something that happens during dreams, that you have all these complex narratives and you think they're very long, but actually they happen very fast. If you measure the time that people get, wake up and they tell you the story. And the same thing also happens during awake behavior. So when the animal sits and sticks, like, as you said, whenever there is this large irregular activity, it's not just during sleep, it's also during, if the animal stops grooming or stays quiet, you have these shockwave ripples, and people checked and they find that there was this replay of the experience. So it's like daydreaming, right? But there is a question. So let me see the question here. Could these observations be related when people say memories are strengthened during sleep? So this is kind of related in a way to the question that Jacek was asking, because yes, one of the theory is that this replay during sleep, and so your dreams during sleep, is a form of consolidation of memory. So what we saw before, the consolidation, one theory is that this is happening during sleep as a way of consolidating are repeating the experience. So like you have your experience and you encode it in place cells, but then you repeat it so many times during sleep, for example, in a very fast way that now you can use that to train another part of the brain that is lower at learning. And now that part of the brain consolidates the memory. So the hippocampus learns everything fast with place cells. But then if something is significant, then at the time of sleep with consolidation, you can transfer that memory to another part of the brain, probably neocortex, by replaying and replaying and replaying that experience. Not the experience, because you're sleeping. So, or you're thinking, you don't repeat the experience, but you repeat the neural encoding of that experience. So that's that in a way kind of answered both of those questions. And one interesting thing is that sometimes people also found sometimes the replay is also done in backward order, and there are theories of why that is, and probably I should have put it here and expanded it, but in the interest of time, I don't want to make it too complicated. So, but you find these replay of experience in the same direction the animal used, and we also find people have done it in open space, in two-dimensional spaces, so like not just on tracks. And there is this result called pre-play, because they noticed that sometimes you find these sequences also during the sharp wave ripples when the animal is resting before the experience occurs. Meaning that in a way, perhaps the animal is planning, imagining the path, kind of planning that path, right? And so this was kind of seen in various studies, but I'm showing one. This is in two dimensions, right? So you see time. So you characterize your place fields in open space, and then you have time. You look at when you have total spike activity density, meaning like you have sharp wave ripples when a lot of cells are active together. See like these huge spikes here. These are total, the sums, that's just the whole population activity. So when you see these events, those are sharp wave ripples. Now you look at, unit number, all the different cells, all these different spikes, right? So you see when the cells spiked all together, when you see these columns here. So you see all these cells fighting. And now you look at what would be the path that those place cells that are being fired during the sharp wave ripple encode based on where the place field was, right? So you make a frame, you divide it in frames, and you look, first the cell that fired here fired, then another place cell that fired here, and then here, and then here, and then here. And so you can kind of reconstruct what path the animal is imagining during that sharp wave ripple. The same thing that basically we're seeing in a single dimension, in a linear track. This is just two-dimensional. It's just the same thing. It's just that now, you kind of have to split it in different maps. And you see like, okay, this is this path here, which is this path here, right? So it goes from here to here. And so that's what the rat is imagining of doing. And they found that that tended to predict what the animal was doing. Not always, but afterwards the animal was following these paths. And they saw that those paths were usually toward what was the home point. So the point that the animal liked to hang out, it's like their home corner, or to a goal location. So I'm not going to describe the whole experiment, but basically there was a way to have a goal location that changed every day. And so the animal was usually thinking about planning a path back to the home point, the home corner, or to the goal location where it would get reward. So very fascinating, right? It's like this is a system that might be involved in consolidation and memory, but also in imagining the future and planning. And so it just so happens, I'm not going to read this because I'm kind of running out of time, but you can read this. Is just pretty clear what's happening in this slide when you read it. Is that people with hippocampal lesion not only have these problems with memories, but they also have problems in imagining things. So here they asked, imagine you are lying on a white sandy beach in a beautiful tropical bay. And so you see the control patient makes a nice description. But the person with the hippocampal amnesic, when you read this thing, is very fragmentary. It's a poor, it shows poor imagination, lack of detail. And so it's like, this is extremely fascinating because you start thinking, okay, memory and imagination is kind of the same thing. Like in a way, okay, not the same thing, let me correct myself, but memory is about reminiscing something that has happened to you. But when you use imagination, okay, you can imagine about something, but then when you try to produce, I say, okay, imagine yourself on a beach. Now you're just imagining, but how can you imagine? You can only fish things that you already seen or you already experienced to some extent, right? You can't really imagine the future. Like if you want to see, go look back at thinking about how people imagine the future in the past. It's kind of funny because, all right, maybe they have something in mind. It's like, okay, maybe people will start going around like this, but then people are dressed exactly like they were back in the days because you cannot imagine the future. What you're doing is reminiscing and maybe imagining one thing new, which was like, okay, these little cards. But then even the style of these cards is kind of old-fashioned, right? It's just there is this mismatch of new and old when you look at what is called retrofuturism, right? So here, okay, they imagine that one day we could draw on a pad, right? But then look, there are these old-fashioned buttons here, and what you write here, it shows on a display that is like such an old-fashioned, low-tech display with these, pixels, and so they imagine something in the future. They had an idea, but then they can only imagine it with what they know, right? Imagination is a form of memory in a way. Same thing with Star Trek. If you're in Star Trek in the 60s, you see these teletransport machines, but then when it breaks down, people go down. Obviously, they're using valve electronics. Valve electronics. It's just whoever knows electronics. It's just like it's an old technology. It only survives in electric guitar amplifiers because it gives you the right sound. But like otherwise, people don't use it anymore. There are transistors now. But they couldn't imagine the transistor, right? So they imagined teletransport, but they couldn't imagine everything. They just have to work with this style and so on and so forth. Just a machine that grinds books and then puts them in people's brain. Oh, that's very advanced and futuristic, right? But here there is somebody that is using a level to just grind things. And same thing everywhere. Here they imagine a robot that would clean, but they didn't imagine Roomba. And so on and so forth, right? So it's just like it's fascinating. I hope this was an interesting lecture because in a way it's showing what is all these plasmas and grid cells being tried related to psychological phenomena, right? So memory, consolidation of memory, declarative memory versus non-declarative memory, so autobiographical memory, your sense of self, your sense of identity built on your episodic memory, and the involvement of the hippocampus, and this idea of imagining, all things that we know the hippocampus is involved. And there are things that place cells do, like remapping or replay or pre-play, that are, maybe we are deluding ourselves, but I think there is a lot of, in the field, we do understand that probably that has something to do with that and might be the key to understand how cells in the brain really do all that. And, you know, starting from a humble model, which is a rat running around with place cells and grid cells, and just trying to get to understand the neural mechanisms of these phenomena that are only, you know, investigated at the psychological level, things like memory, declarative memory, imagination. So this is just kind of like a recap. You know, you get, okay, I just gave you more slides to understand. So it's like, you know, the rat running, you have theta, you have, you know, different place cells, the spike in different regions. And then you have pre-play, would be the one that very quickly recapitulates the trajectory that is about to happen. And replay, it just does the opposite. And here I gave you one of those examples where the trajectory is recapitulated backward, okay, backward. So there is, you know, forward and backward. This is basically a slide that summarizes some things that basically I already said, how, to what extent this replay is probably linked to this idea of how replay repeatedly reactivates mnemonic representation in the absence of behavioral repetition. So this activation continuous time experience, for example, during sleep. This might promote associative learning in other areas of the brain, like, for example, neocortex. And so then you have that kind of consolidation, right? And then replay awake state might be memory-guided decision. So path planning, we saw the rat that was imagining paths to the goal. So it knows where the goal is, and now it's planning a path to the goal. So it's a memory-guided decision. In a way, planning is memory-guided, or even mental travel that is temporally compressed, either for memory or replay. The last part of the lecture that I'm going to skip, I was planning to skip anyway, and we are 5:15, so that's kind of good. As usual, I can stick around if you have any questions. Let's see. Very interesting class. Okay, great. I'm glad you liked it. And yeah, if you have a question, unmute yourself and ask the question, or, you know, if you wanna have office hours, I'm here. Let me know, and I'll stick around. And otherwise, you're free to go.
Thank you, Professor. Have a good week.
Thank you. You too.